Okay, before we start the tutorial, let's begin with a summary, right? So tonight we are doing Fourier series, okay? Now, when we talk about Fourier series, we are talking about a Fourier series of a given function. And this function here, it is of a period 2p, all right? It is a periodic function, okay? Yeah, so whenever we talk about a Fourier series, the function must be periodic, okay, right? And what is the Fourier series? What does it look like? So it's actually an infinite series, and it looks just like this. Yeah, so you see, you have this a0 over 2, and then plus this summation, n from 1 to infinity, right? Yeah, so it's an infinite series, okay? Yeah, and of course you can see inside here that do you see this p here? You know where my cursor is? Then here also got a p, right? So this p, what is this p? Well, then we know that the period is 2p. The function, the period is 2p. So it's actually the same p, right? Now, all these a0, an, bn, these are called Fourier coefficients, and these are the formula. Okay, so a0, an, bn, the formula here. Now, of course, if you see here, inside the formula, you can also see the p, right? You see n pi t divided by p, right? So all this p here, they are also the same p as the period 2p, right? It's the same p. Okay, right. Okay, so this is the formula. And if we look at all this, we see that actually it's like integration, right? Yeah. Now let's look at the range of integration. So you realize that it's a c to c plus 2p. Okay, c is actually a constant. Yeah. So c to c plus 2p. So therefore, what is the interval of what is the length of the interval of integration? So obviously it's a c plus 2p minus c, right? So actually the length of the interval of integration is 2p, is the period. So we can say that we are integrating over one period. It's okay? Yeah, we are integrating over one period. Yep. Now, in our problems, all this one period, they are mostly like that. So it's minus p to p or 0 to p or 0 to 2p. All right, so this is one period. So in most of the cases, it's either we integrate minus p to p or we integrate 0 to 2p. Okay, as to which one we use, it's very clear from the question. All right, so usually the question will give us one period of ft. Then we just look at that period. What is the period that they give us? If they give us in the form of 0 to 2p, then obviously you integrate 0 to 2p. But if they give us in the form of minus p to p, then we'll just integrate minus p to p. All right, so this is quite easy to decide which one to do. Okay, so this Fourier series. Then the next thing. Now, this Fourier series actually, when you say that the Fourier series of a periodic function is this, what exactly do we mean? All right, is the function equal to the Fourier series or not? So actually it is, all right, the function actually is equal to the Fourier series, all right? At those points when your function is periodic, yeah. So you see at the points of discontinuity, so when your function ft is discontinuous at some point, right? Yeah. So we say that this periodic function, sorry, I forgot to show you this. So we denote the Fourier series of ft as capital F, okay? So at the points of continuity of this small f of the function, actually the Fourier series and the function, they are equal, all right? So that means you are able to express the function in infinite series, okay? So this is at the points of continuity. And then how about at the points of discontinuity? Now, actually, that point is here. Okay, so at the points of discontinuity, so suppose we call it T naught. Okay, so ft is not continuous at T naught. Now, over here, your Fourier series at T naught, actually is half of ft naught minus plus ft naught plus. So this is actually ft naught minus. It's like the left hand limit at t naught, and then this one t naught plus is like the right hand limit at t naught. Okay, so actually is this plus this divided by 2. So you can say that it is the average of these two values. All right, so this is your, f at t naught. The big F is the Fourier series. Okay, yeah. So in this case, your ft naught, the small ft naught actually here is not defined. Okay, because it's not continuous at t naught, right? So your ft naught here actually is not defined. Okay, but the capital ft naught is equal to this value, right? So therefore, if we want our Fourier series to be equal to the function for all t, then what do we do? Now, at the points of continuity, no problem. They are equal, right? But at the points of discontinuity, how do we make it equal, right? How do we make it equal? Now, we already know that Fourier series at t naught is this value, right? So then what do we do is that we go and define at the points of discontinuity, we also go and define the small ft naught to be equal to this. So that this value is the same as this value here, right? So then we can say that your ft naught, the small ft naught, is also equal to the Fourier series at t naught. So that means at t naught, they will also be equal. Okay, so this is our conclusion here. So once you do this, once you define at the points of discontinuity, define the function value to be this, then you can say that your ft, the function, is equal to its Fourier series for all t on the real line. Is it okay? All right. Any questions here? Oh, I see the chat here. Why you got so many people? Oh, what is it? Okay. Yeah, looks like it's not asking me anything, right? Okay, class, any questions here? If there's question about this, about this point here, you just unmute and ask me. Okay. Well, looks like everybody is okay, right? Okay, so now then we go to our first question. So here we want to find the Fourier expansion of the periodic function. So you notice the function must be periodic, right? Otherwise you cannot talk about Fourier series. Okay, this periodic function whose definition on one period is like that. All right, so they give you this, and this is the one period that they give you. Is it okay? So t from 0 to 1 is one period. Okay, here, class, first of all, if they tell you this one is one period, right? Well, what is the period? Well, basically, I want to know the small p. Actually, what is the period there? Function ft of period 2p, right? So over here, what is your 2p? What is the period here? Period. So the period here, there's a 2p, right? Yep. So what is it equal to there? Yeah, class, anyone? What is the period here? The period 2p here, what is it? Yeah, any idea? Hey, class, they tell us, yes, it's 1. All right. Yeah, I cannot type. So it's actually 1. We type here. So it's equal to 1. All right. So we see t from 0 to 1, right? So the length of this interval is 1. Okay. So the period here is 1. So that means here we know the small p already, right? So we can go and find the Fourier series. Now let me show to the solution. Okay, solution is here. All right. So I want to find the Fourier series, right? That means I need to go and find what? I need to go and find all the A0, AN, BN, right? Okay. Before we do that now, because I want to see, whether this function has points of discontinuity or not. So therefore, before I do that, I want to go and sketch this graph. Okay, now what's the function here? Okay, e to power minus t from 0 to 1. So we go and sketch that. So 0 to 1, you can see this is a t-axis, right? So 0 to 1, so you sketch e to power minus t. So it's actually this portion in green. Is it okay? Yeah. Now this one is 1 period. Now since the question says that the function is periodic, right? Now what's the meaning of periodic? Periodic means well, it repeats itself. Okay. So this one, you go and repeat this this curve here. So you repeat here, or you can do it here, do it here. Okay, all right. So therefore, this is what the periodic function looks like. Is that all right? Okay, so this is what it looks like. Now, looking at this graph, now you got your graph here, right? Can you tell me what are the points of discontinuity there? Can someone give me a point of discontinuity? Point of discontinuity? At which point the function is not continuous? Okay, how to see continuous or not continuous? Basically, when the function is not continuous at a point, the graph breaks. All right, the graph breaks. Okay. Well, I mean continuous, everyone knows the meaning of continuous, right? So that means no break. All right. So if the graph breaks, that means at that point, the function is not continuous. So you look at your graph here, you got like that, you got like this, and you got like this, right? Is there a place where is there some points where the function breaks? Can someone give me some points?
0.0.
Yeah, 0. Okay, so everyone can see this or not? 0.0. Because you see you got 1 point here, right? And you got another point here, right? Yeah, so you see the graph breaks. All right, so you say it's a 0, then obviously 1 also, because you see 1 also, it breaks, right? Then 2 also, then you can imagine 3 as well, right? Then -1, -2, -3. So that means at all the integers. Yeah, so all the integers, these are the points of discontinuity. Is it okay? Yeah. So later on, you of course at the points of discontinuity, we want to do something special, right? Yeah. Okay, so let's carry on from here. So let us first go and calculate A naught. Okay, let's look at the formula for A naught. See, A naught is like that, right? Now here, the integral. Now I say the integral is what? Is you integrate over one period. So it's very clear from the question here. Now they say this one period, right? Then you just integrate 0 to 1. So basically, you integrate 0 to 2p. So this is like 0 to 2p. Okay, so therefore you see, I put here 0 to 2p, right? Then you really go and put that in. This is your ft, right? Your e to power minus t, right? Then you go and integrate. Okay, so A0 done already. Now I go to AN. This is the AN formula. So AN, so this is AN, right? Yeah, integrate 0 to 2p. And then I'm going to put in the FT. Of course, our P is half. 2p is 1, so P is half. So we are getting this. Okay, now this one here, actually to carry out this integration, actually need to do integration by parts. All right, now of course that one not so easy. So actually in our notes, we actually have some formula. This formula is inside our notes, right? Our lecture notes. Then we can apply this formula. Now all these formula, they are actually obtained from integration by parts. All right, so we see this one here. Looks like we can use the last formula. Use the last formula here. Okay, so if you use the last formula, then you'll be able to get all these. Yeah, and then we put in the limits. Okay, so put in the limits and we simplify, then we get to here. All right, so this one we need to go and practice, go and do it ourselves. Now you see that I highlight these two items, right? Now sine 2n pi, cosine 2n pi. So what are the values? Well, if you know already, right? Sine integer pi is 0. Then of course sine 2n pi is also 0, right? 2n is also integer, right? Yeah. So sine 2n pi is 0. Then cosine 2n pi, well, if you don't know before, well, today you know cosine 2n pi is actually 1. Okay, all right. Any questions until here? Okay. Right. So then the next one, we want to go and find Bn, right? So see our Bn formula here. Okay, so this is our Bn. And of course, we go and put in our Ft, then get something like this, right? And of course, how to integrate this? Well, actually, it's integration by parts. This formula is also inside our lecture notes. So just go and apply. Okay. Yep. So this is what we have. It's okay. So I won't explain all this. So we need to go and practice ourselves, really go and substitute in the values, go and manipulate all this and make sure that we can get the correct answer. Is that all right? Okay, so that's the end. All right, so it looks like we got A0, AN, BN already, right? Then what is the next thing to do there? Now, of course, the next thing is to go and write down this Fourier series. So we go and write down the Fourier series. So that's according to this, okay? You are looking at the left side, the Fourier series here, right? So that's exactly how we write it down, okay? But that's not the end yet, because just now we already know that our function got points of discontinuity, okay? And we also know just now from our summary, if we want our Fourier series to be equal to our function for all t, then what do we do there? So at the points of discontinuity, we must go and define our small f at t0 to be this, the average of these two values, right? The average of the left hand and right hand limits at t0. Okay, yep. So that's exactly what we are doing here. So we say at the points of discontinuity, t equal to t0. So our t0 is the integers, right? All the integers. So we go and define ft0 to be this. Okay. Now how to get these two values? Ft0 minus, ft0 plus. Well, let me draw a diagram. So actually it's like that. Your t0, say is this point. Your t0 is here. Right? This your t0 here. So of course you got your function here. Maybe your function is until here, okay? And then because it's a point of discontinuity, right? So maybe the functions start from here, right? Okay, so say it's like that. Right? So it's like this, Yep. So what's the meaning of ft0 minus? Ft0 minus means, now minus, everyone know what is the meaning of minus, right? Minus means what? Less than t0 or more than t0? Hey, class, minus means what? More than t0 or less than t0?
Less than.
Yeah, it's actually less than t0, right? So less than t0 means, you know which side is less, right? So this side is less than t0. So that means it will approach t0 from here. So you can see that it's all the time less than t0. So you approach t0 from the left. So that's why they call it left-hand limit. So you approach t0 and you approach from the left side. So that means you get closer and closer to t0. And then you see what is the value at slightly less than t0. Okay, so I think if you look at this diagram, you can see already. You approach closer and closer to t0 from here. Then actually, what is the value? Actually, what is the value? Then you know that the value is actually here, right? This is your ft0 minus. Can everyone see it? You approach t0 from the left. Actually, what is the function value? That means you are doing this, right? You are coming in this direction, right? So actually, it's this value here. Okay, Then how about ft naught plus? Now ft naught plus is the other way. Ft naught plus meaning that you approach t naught from the plus side. Plus side means more than t naught. So it's approaching t naught from the right side. So that means like this. Okay. So it's like, this is your function, right? So you follow, approach t naught from this side. Then wow, very, very close to t naught, but still a little bit more than t naught, right? So then you can see the function value. So the function value here is this one. Is it okay? All right, so this one is your, this one is actually your, this one, ft naught plus. Then this value here is actually your ft naught minus. Is it okay? This one is ft naught minus. This one is your ft naught plus. Okay, now, so it's actually the average of these 2 points. Right, so this plus this over 2 is actually the average of these 2 points. Okay, so if we, well, it's e to the power minus 1, e to the power minus 0, right? So let's go to our graph to see just our graph. I see our graph. Now, for example, the average of these 2 points, right? So meaning which point? Meaning this point here, and this point here. Yeah, so these 2 points. So you can see this is ft naught minus, which is the e to the power minus 1, and your ft naught plus there actually is e to the power 0. All right, so it's the average of these 2 points. Is it okay? Yeah, so that's why we have this. All right, now, so now our answer is complete. So once you make this definition, then we see from our summary that, once you make this definition, then we can now say that your function ft is really equal to the Fourier series for all t. Yeah. Okay, any question, class? Okay, so looks like all right, y'all. Then we go and see the next question. Yep. So the next question, we also want to find the Fourier expansion of the periodic function. You see here, periodic function again, whose definition on one period is like that. Okay, so ft is 1 plus t, and where is your one period? T from minus 1 to 1. So this is a 1 period. Okay, yeah. So from here, can y'all tell me? Now the period is 2p, right? Yeah, so that's our notation. And in this case, your period is how long? Your period from minus 1 to 1. How long is it? Any idea? From minus 1 to 1, how long is this interval? Class?
2.
Yeah, it's actually 2. You know how to get 2, right? You take the upper limit minus the lower limit. So 1 minus minus 1. So that's how you get 2. Is it okay? All right. So 2p is 2. So that means your p is 1. Okay, yeah. All right, so that's the first thing. So let's go and do this first. Go and find this Fourier expansion. All right. Okay, once again, we want to go and draw the graph of this, right? Because we want to see whether got points of discontinuity or not. Okay. Okay, so I actually go and draw from minus 1 to 1. So everyone can see here, right? Yeah, minus 1 to 1. So 1 plus t. So it is actually a straight line. So, well, periodic means that you go and repeat this pattern. You see, you repeat here, you repeat here. You want to repeat some more also can. Yeah. So in fact, you can repeat some more. You repeat some more here. Then here you can also repeat some more. Okay. So you get this. All right. So from this graph, then you can tell already. Are there points of discontinuity there? Do you see points where the function breaks? Yeah. Can you give me some points where the function breaks? Anyone? Yeah, class. You all see points where the function breaks, eh?
-1.
Yeah. So you can see that here it breaks, right? So you can see, well, you got a point here, but you also got a point here, right? So you see it breaks. Oh, yeah. So these 2 points here. So this is the value here is 0, the value here is 2. So then later on we know already, yeah, average of these 2 points, right? 0 plus 2, then divide by 2. Okay, so later on we'll define it this way, right? So it's not just -1 now. So we can see, oh, 1 also. Yeah, then you can see 3 also, right? Then you can also, you can imagine one, right? So 3 also, then later will be 5. Then here -3, then -5. All right, so it's like +-1, +-3, and so on. Okay. All right, so now we determine the points of this continuity already, right? So let's go back to go and find the A0. Okay, A0. Now it's 1 over P, then you integrate over 1 period. Now here, our 1 period actually is -1 to 1. Okay, so it's -1 to 1. And we also know that P is 1, right? So this is the case minus P to P. All right, so it's just -1 to 1. Okay, so well, here we go and integrate all. Yep, so we put in the function, then go and integrate. Okay, yeah, then we want to do the AN. Okay, AN is like that. So also integrate -1 to 1. Okay, put in the function. Yeah, so you put in your 1 plus t, right? Then of course you want to integrate this. So what we do here is you can go and multiply out first. You go and multiply out like that. Yeah, then you can integrate. So cosine n pi t, well, this one we know how to integrate. And then the t cosine n pi t, well, this one actually is integration by parts. But your lecture notes already got the formula, right? So this one you just apply the formula there. Okay, so go and do it. You can see that everything is integration here. Okay, then it turns out to be 0. Okay, so here there are a few things. There are a few things here, things like sine n pi, sine minus n pi, cosine n pi, cosine minus n pi, right? So what are these values? Okay, sine integer pi is 0. You don't care whether the integer is positive or negative. All right, sine n pi, sine minus n pi, they are all 0. And then cosine n pi is actually -1 power n. All right, cosine minus n pi actually is the same as cosine n pi because cosine is an even function. All right, so it's also -1 power n. Is that all right? Yeah. So that's an. Then we want to do bn, right? So this one is bn. Then we also go and do this. Now, of course, we also want to go and multiply out, right? Yeah. Multiply out, then go and integrate. Yeah. So then, it will give us this. All right. Okay, now. All right. So we got A0, AN, BN ready. So now we go and write down this Fourier series here. So go and write it out, write down nicely. So we have this. Okay. And that's not the end because we've got some points of discontinuity, right? So earlier on, we know that it's +-1, +-3, right? So you know that at these points, you must define the function value to be like this. Average of the 2 points, all right? The left-hand limit and the right-hand limit. And we go back to the graph. Just now we see I draw these 2 points, right? So this one, the value is 0. This one, the value is 2, right? So 0 plus 2 over 2. So you see, 0 plus 2 over 2. So this is how we define it. All right. So once we have this, then our answer is complete. Okay. Any questions until here? Okay. So no question, right? So no question. Let's go and do part C first. Now part C is like that. If ft is capital Ft, denotes the function defined on the real line by the Fourier series of ft. All right. So this capital Ft there actually is a Fourier series of the function in part A. All right. Then you want to find these values. What is f1, f minus 5, and here we have f0, right? Yep. So we need to find all this. Okay, now. Okay, so they denote the Fourier series by capital F, right? So just now we got the Fourier series here. Right, everybody looking at the right side here. You see, this is actually our Fourier series, right? So this one, the right-hand side is the Fourier series. So part C, they call it a capital Ft. All right, so we actually have a small ft equal to capital Ft for all t. All right, for all t. Yep. So now we want to get f1. Okay, f1. See f1 here. Let's go and do f1 now. Let's go and get f1. Now f1, you type here f1. So f1 should be equal to f1, right? All right, because the Fourier series and the function they are equal at every t. So big f1 and small f1 are the same, right? And we also realize that this 1, the point 1, when t is 1, actually it is a point of discontinuity, right? And you see points of discontinuity plus minus 1. So 1 is a point of discontinuity. All right, so what is this value? What is this value then? Well, actually you define it already. And you see your ft naught, you define it to be what? You define it to be 1. Okay, so therefore here, this is 1. Make sense? Is that okay, class? All right, now. Any questions? Okay, then same thing. How about your f minus 5 then? Now your f minus 5, that's the next term that you need to find, right? So it is also equal to small f at minus 5. Now, what is a small f at minus 5 there? Anyone give me? Anyone tell me the answer? What is the small f at minus 5?
1.
Yeah, it's also 1. All right. How do you know 1? Because it's here, what? Your ft naught is 1, right? Minus 5 is also a point of discontinuity. So you see this one is also 1. Right. And how about f0 then? What is f0? Then you say, hey, this is also small f0. Right, also small f0. Now, what is small f0? Do we know what is small f0, class? 1 equal to 1. 0, is it a point of discontinuity? 0, is 0 a point of discontinuity?
No.
Yeah, it's not, right? So what is a small f0?
So 1.
Also 1. Then this one also 1. Where you get the 1 from? Actually it's 1, but where you get this 1 from?
Graph.
From graph. Okay, yeah, from graph, yes. Another way there is
Function.
yes, from function. Because everybody see this? ft is 1 plus t. T from minus 1 to 1. Can everybody see on your left side here, the question here? Small ft is 1 plus t, t from minus 1 to 1, right? Now, 0 is between minus 1 to 1. Yes, yes. So therefore, f0, then you just substitute 0. 1 plus 0. So actually it's 1 plus 0 plus 0. So therefore it's 1. Is that okay? All right, not? Yeah, so that's why it's also 1. Everybody clear or not? I hope you are clear. So any questions, you just ask me. Yeah, so now you know all the 3 values already, right? Yeah, I just go and put in. Okay, any questions? Okay, right. Okay, so then now let's go and do part B. Okay, part B is using the Fourier series of ft obtained in part A. You want to find this sum. This kind of question also quite common. They ask you to find Fourier series, right? And then ask you to use the Fourier series to go and find sum of some series. Find the sum of some series. Okay, so this is an infinite series. Hey, let me rephrase the question. So your part B actually is this. So that means from your 2A, this is the Fourier series that you obtain. Right, then it's actually this one. Okay, yeah, so ft equal to this Fourier series, right? And then from here, how to get this sum? Okay, how to get this sum? So how to get this sum from the Fourier series? What do we do? So, okay, now you see here, your ft equal to this, right? Then here you got an infinite sum, right? So obviously, if you want to get an infinite sum, the infinite sum has to come from here, because this is the only place where you get an infinite sum, right? Yeah, so this is the only place you get an infinite sum. So that means this one has to come from here. Is it okay? Yeah, makes sense? Quite intuitive, right? Yeah. And then after this, you notice that this one involves t, involves the variable t, right? Involves the variable t. But of course here in this series, there's no t. So that means your t here, the t here, the variable t here, you need to substitute some value. Okay, you need to let t be some value. And then you need to guess what value. Okay, so that when your t is equal to that value, then this thing will give rise to this. Make sense? Yeah. So this is how we do it. Yeah. So basically, is over here you go and substitute the t as some value, and then hopefully this infinite series here can give you this. Is it okay? All right, all. Okay, so now we know we need to substitute some value of t, right? So you need to guess what value of t to substitute. Okay, guess what value of t. Yeah, so you need to guess. Yeah. So then of course we must make some intelligent guess, not anyhow guess, right? Yeah, make some intelligent guess. So first of all, this t, this value of t, surely it must be should be a nice number. Because if the number is not nice, then how to guess, right? So do you think the t can be something like that? Do you think the value can be something like this? Do you think this will be the correct value? Then of course cannot be, because if the value is this, then who can guess, right? Then no one can guess. So therefore, surely the value must be quite a nice number, right? So you go and look at nice number. Maybe you all tell me what number is nice to you. Anyone? What number is nice? Can you say again? Yeah, what number is nice to you?
Half.
Half. Yeah, half. Half is the correct answer. But before you guess half, won't you be guessing some other even nicer number? Probably half may not be your first guess, right? Actually, what is your first guess?
Half.
Hey, half is actually not so natural, right? Half is
to try to get a value from sign.
Yes, you try to get a value from sign. All right.
And
so
there's
actually,
only half or.
If you say a nice number, then why don't you put 0 then? 0 also very nice one.
But you'll be 0.
Yeah, precisely. 0 is a nice number, but if you put inside all, you're going to get sign 0, which is 0. So you get summation 0, right? So it's not going to give you this. So then 0 cannot. Yeah, 0 cannot. Then you want to say, how about integer? Integer also very nice, right? 1, 2, all this integer. All right, integer. So can it be integer leh? Can t be integer? If t is integer, what happens? Yeah, if t is integer, what is sine n pi times integer leh? Anyone?
Also 0.
That's right, also 0. Because your n here is also an integer. So integer times integer also integer, right? So you get sine integer pi lah. So you also get 0. Right? So you know that t cannot be equal to this. Yeah, so t cannot be 0, cannot be integers. All right, so therefore, then I guess cannot be integers. So therefore, then you want to look at maybe fraction. So that's why you are thinking that how about p equal to half, right? Yeah, because integers cannot. And what are other nice numbers? Then maybe fractions, right? So maybe half. Well, actually, why half? Well, if you say 1/3 also not bad, right? But why half? So actually, this one is a trial and error, right? You really need to go and try out and see that it really can give rise to this series here. Okay. Okay, so I'm going to substitute t as half. Is the correct choice. Okay. So that means I'm going to get what is sine n pi over 2. Okay, I'm going to get sine n pi over 2. So I need to find this value, sine n pi over 2. Is okay? Here your n is integer. Yep, your n is integer. Then you see here, your n is 1, 2, 3, 4 until infinity, right? Okay, so your n is integer. So what is sine n pi over 2? So here I actually show you the sine x. This is the graph of sine x. All right, so here I actually draw 2 periods of sine x. 0 to 2 pi is 1 period, and 2 pi to 4 pi is another period. Okay, so from here you can see if n is 1, if your n is 1, I put here when n is 1, then this one everyone knows, right? When n is 1, what is sine n pi over 2? That means sine pi over 2. You know what is sine pi over 2? No, sine pi over 2. Hey, class, do you know what is sine pi over 2? You are looking at the graph here. Can you tell me what is sine pi over 2?
1.
It's 1. Okay, so actually it's here, right? Yeah, this is your sine pi over 2. Yeah, so this is actually the point, right? Yeah, pi over 2 is here. So we know the value is 1. Okay, so this is 1 when n is 1. And then we will use this. Now, because your sine x is periodic. So when here you get the value 1, then you will know that 2 pi later, because the period here is 2 pi. Okay, so 2 pi later, this pi over 2, right? So 2 pi later, when you are here, you will get the value 1 again. You will get the value 1 again. And of course, 2 pi later, somewhere here, which I didn't draw, you will get 1 again. All right. So this point here is pi over 2. This point here will be pi over 2 plus 2 pi. All right. So whatever this value is, you cannot type here. So can I type here? Okay. So whatever this value is, maybe I call it star. All right. Then this value here will be a star plus 2 pi. Is it okay? So that's the meaning of periodic. Yeah. So this value pi over 2, right? So this point is actually pi over 2 plus 2 pi. Okay, so pi over 2 plus 2 pi, actually it is 5 pi over 2. So when n is 5 pi over 2, the value is also 1. Right? So then you keep on adding 2 pi, and you get 9, 13, and so on. Okay, so for these ends, sine n pi over 2 is 1. It's okay? Yeah. And then, okay, so this is like well, you can say odd numbers, although some are missing, right? Yep. How about when n is even? If n is even, then what next? If n is an even number, what is sine n pi over 2? Yeah, what would that be? Yes, class, when n is even times pi divided by 2, sine even number times pi over 2, what is the value?
0.
Yeah, it's actually 0, okay? Because you're going to get sine integer pi. All right, so this one even. So looks like I'm still short of some numbers, right? Okay, I see that there's some point here. Here, this point is actually, because the value here is -1. This is actually 3 pi over 2. All right, 3 pi over 2. Hey, yeah, just now we didn't have n equal to 3, right? Yeah, so maybe now we should look at when n is 3. So we need to look at all the n, no? So n is 3, so sine 3 pi over 2. So you know I'm getting -1, okay? So this value, sine n pi over 2 is -1. Okay, so here, so same thing, periodic, right? Yeah. So if this number is so let me call it a symbol. Call it what symbol? Okay, call it this one, dollar sign. All right, then we'll know that over here, 2 pi later at this point, this will be the dollar sign, and then plus 2 pi. Is it okay? Yeah. So over here, you will also get the value -1. So that's the point. Right? So this is 3 pi over 2. So 3 pi over 2 plus 2 pi. So that will be 7, right? 7 pi over 2, right? Yep. So this is 7. Yeah, 7. So that's the next point. Okay. So if you keep on adding 2 pi, you will get the next point will be 11. Yep. Then the next point will be 15, and so on. All right. So now if you check, I think we have exhausted all the integers, right? 1, 2 is even, and then 3, 4 is even, then 5, 6, then 7, 8, 9, then 10, then 11, So we already exhausted all the integers. All right, and these are the 3 values of sine n pi over 2. Is it okay? All right, so let me write this down. Okay, so if we go and write this down nicely, so this is what we have. All right. Yeah, so n even, this is 0, and then this is 1 and -1 for these values of n, right? Yeah. So now I'm going to substitute t as half in the Fourier series, right? So that's what you all mentioned just now. Okay, so this is actually the Fourier series with t equal to half. So I have a ft, so that's half. And then this is a sine n pi t, right? So the t is half. Okay, so that's what I get. All right. Okay, then the next thing is I'm going to write down what is f half. Okay. Yeah, no, f half is equal to this Fourier series. But I also want to find it in another way. What is a small f at half? Okay, can someone tell me how to get the small f at half? Any idea how to get small f at half? Yes, class?
Sum in the function.
Yes, from the function. Right. So we see your ft is 1 plus t, right? T from -1 to 1. Okay, now half. Now I'm looking at f half. F half. Half is inside -1 to 1 or not? It is, right? Yeah, half is inside. So therefore, I can just substitute. So f half is going to be 1 plus half. Okay, yeah. So f half here is just 1 plus half. Okay, so well, it's just 3/2. And of course, the reason here is because of this function here. All right, okay. So actually, this is the situation now. I have this Fourier series. Fourier series is here. And it's equal to 3/2. Is that all right? Yep, it's equal to 3/2. So what I do now is this one equal to this, right? So I'm going to shift the 1 to this side. So if I shift the 1 to this side, then 3/2 minus 1, right? So that's why I get the half here. Okay, and over this side there, you will have the 2/pi, and you have this infinite series here, right? So this is actually the infinite series. Let me change the highlight. Okay, so this infinite series here, this one that I highlight, actually will give me this. Yeah, it will give me this. Okay, how I know it give me this? Well, you just go and put in your n. When n is 1, you are going to get sine pi over 2 over 1 minus 1 square. Okay, so it's just sine pi over 2, so it's 1. Then when n is 2, you are going to get 0. And then when n is 3, you are going to get -1 power 4. Sine 3 pi over 2 divided by 3. Okay, sine 3 pi over 2 is -1. So you are going to get -1/3. All right, so you just go through all this n equal to 1, 2, 3, 4, and so on. Then you will be able to get this. All right, now. And this is the series. Notice it's the same series here. Same as your part B of this series. So yeah, you actually got the series already. All right, so what is this sum? And your 2/pi, you just divide over. Okay, any questions? Okay, so looks like it's all right. So that's number 2. So let's do the next one here. Okay, right. Okay, so before we do number 3, let's go to our summary. Okay, the next thing that we are going to talk about is about Fourier series for even function and odd function. Okay, so before we go into that, let's see what is an even function. Now, even function, you say some function is even, you actually mean this. Your ft is equal to f minus t. Okay, yeah, ft is equal to f minus t. Let me give you some examples. For example, t square, right? For example, cosine t. So all these are even function. Because t square, or maybe you bracket minus t and then square it, it's the same, right? Yeah. Cosine minus t, cosine t are the same. All right. Now for even function, there's we can easily see this from the graph. Okay, so let me show you the graph of an even function. So I'm actually plotting here t square. This graph we are very familiar with. All right, this is actually ft equal to t square. So we can see that this graph is symmetrical about the vertical axis. All right, so the graph here, it's very obvious. It's a symmetrical about the vertical axis. All right, so because of this, we can actually very easy to know. That means you no need to go and prove this. You can actually see from the graph, and you one look, then you can say that, oh, this function is even. Okay, because it's symmetrical about the vertical axis. Right. Now, what about odd function? Now, odd function actually is like this. Here your f minus t is minus ft, right? So you see the difference. So it's like that. Now example, ft is t cubed. Well, that's an odd function. Okay. Or sine t is also an odd function. Yeah. And you want to say, hey, what about the graph? The graph. Here I'm actually drawing the graph of y equal to t cubed. This is t cubed. All right. Then you look at this graph. Is it symmetrical about anything there? No, it's not symmetrical, right? It's not symmetrical about x-axis. It's not symmetrical about y-axis. So it's not symmetrical. So therefore, well, I mean, if you got a graph like that, then at least you also know that this is not even, right? Okay, but it may not be odd. Yeah, but this is certainly not even. Okay, so now we know even function, odd function already, right? We know the meaning already. Now we want to look at the Fourier series for odd function, Fourier series for even function. Okay, if ft is an even function defined on the interval minus p to p with a period of 2p, okay? Yep. Then what about the Fourier series? Now the Fourier series here, let me show you the formula first. Now ft is like that. This is the Fourier series. Okay, so here this is your a0, here this is your an. Okay, so this, your a0 is like that, your an is like this. So if we look at this, I mean, you look at this, where does all this come from? Now all these they actually come from just now our general Fourier series. Okay? Yeah, here. Actually, it comes from here. All right, just that in the special case when your f is even function, then this one will reduce to the one that I show you. All right, how it reduces to the one that I show you there is basically we are doing things like if your f is even, then you know cosine also even, right? Then even function times even function is even function. All right, so that when you integrate minus p to p, basically there is it's like you just integrate 0 to p and then times 2. Yeah, so basically it's like you integrate here minus p to p, right? So it's like here minus p, right? This one is like p, right? Integrate from here to here. So it's like area under the graph, right? So actually there is just like, you can see symmetrical, right? So actually it's like you integrate 0 to p will do, and then you go and times 2. Yeah, so initially it's like that, right? You know that this is the area that you are going to get. Yeah. And then now what you do is you just integrate 0 to p, and then you multiply 2. Then you will still get this total area, right? Okay, yep. So we are using that kind of principle. So therefore, just now our Fourier series there becomes like this. Okay, now there's no bn here because the bn happens to be that it's a ft times sine, right? So if your ft is even, then your sine is odd, right? So even times odd there, you are going to get odd. What happens to odd function when you integrate? Here, odd function, see, you integrate from, say, your minus p here, and then here is your p, right? You find that it is a negative area, a positive area, right? And they are equal to each other. So cancel off, so become 0. So here, if you integrate minus p to p, you are going to get 0. See? All right, so it's based on that. So therefore, you see your bn here actually is 0. So this is our Fourier series. And then our Fourier series here, because bn 0, right? So you don't get the sine term. There's no sine term here. You see only cosine term, right? So therefore, we also call it another name. We call this a Fourier cosine series. This one is Fourier cosine series. All right. Then the next one is, how about if your ft is an odd function, okay, defined on the interval minus p to p, and the period here is 2p. So here, also the same thing. We go back to just now our Fourier series. Then you go and see, oh, now your F odd. No? So if odd times odd becomes even. Okay, so odd function times odd function will give you even function. Right? Yeah. So then you use that and you find that this time all the A is 0. A0 is 0, AN also 0. Because there your FT odd, right? Then your cosine even, right? So odd times even is odd. All right, and then you integrate minus P to P, right? So you're getting 0. Okay, but the B here, this one odd times odd, sine is odd. FT also odd. So odd times odd will give you even. Okay, so then you know even or you integrate minus P to P. Well, it's the same as you integrate 0 to P, and then you multiply a 2 outside. All right, so therefore, this is the Fourier series. So the ANs are all 0. So you see, you only got BN, right? So that means you only got the sine term. So this has another name. We call it the Fourier sine series. Is it okay? All right. So this one is for even F. This one is for odd F. Yeah. All right. So if you have even function, odd function, then you realize that when you find Fourier series there, it's simpler. Because like for example here, you don't need to find Bn because Bn 0, right? Then here there, you don't need to find A0 and An. Right? Okay, so let's go and look at this problem here. Consider this periodic function given in one period. All right, this one is a periodic function, right? Yeah, it's a periodic function in one period. Okay, so this thing is periodic. This is one period. So this is our one period. So the moment you see this minus something to something, right? So this is like minus P to P. Yeah, so our P here actually is 1/8. So okay, all right. So here you can tell that your P is 1/8. I see. Okay, here is taking absolute value. So here you want to find the Fourier series. And then part B, actually, if you can do part A, then part B also can do. Write down the first 4 non-zero terms. Okay, right. So let's go and sketch the function. Yeah, every time we do Fourier series, go and sketch the function. Okay, this is one period, minus 1/8 to 1/8. And I'm going to draw this sine 8 pi t, and then absolute value. All right, so this is what it looks like. Before you draw the absolute value, actually this part there is below 1. Before you take absolute value, actually this part is below. Okay. Then after you take absolute value, then you flip it up, right? So that's why now it comes like this. Yep. So now it becomes like this. All right. So this is one period. So you look at this one period here. Now you look at this graph. What does it look like? This one looks like what? One looks like McDonald or not? And this one looks like McDonald, right? You all know McDonald or not? McDonald is the M, right? This one looks like the M, right? So you can see that it's what? Symmetrical about the vertical axis. So that's why you say that your ft here is an even function. Okay, so that's how you know it is even. Without going through, you substitute t and minus t inside, ft equal to f minus t, right? Of course, you can do that also. But by looking at the graph there, because of the symmetry about the vertical axis, so you can say that your f is even. All right, so that means your bn will be 0. Okay, and another thing to say here is that, now you see this is your graph. This is your graph. So this is one period, right? So I'm sure you can imagine. Can you draw other periods there? Can you repeat the pattern? Can you repeat the pattern? Then sure can. And you can also draw like that, right? You can draw like that. And here you can also draw like this. So this is really McDonald, right? Yeah, McDonald. So here got 3 McDonald's. So here, I mean, you draw this. Are you able to see got points of discontinuity or not? I mean, one reason that we want to draw the function is also we want to see more clearly whether there are points of discontinuity, right? Yeah. So here, can you see the points of discontinuity? Are there points of discontinuity, class? What do you think? Yeah, are there points of discontinuity?
No.
Yeah, so actually here don't have. Right, so that means if no points of discontinuity, then of course later on, no need to define, all right, at the points of discontinuity, because don't have, yeah, no points of discontinuity. Okay, so then we just proceed. All right, so the first thing is this one even function. I go to our summary, okay, even function. So we are going to calculate the A0, the AN. See, this is my A0. See, follow the formula, right? Okay, here, there's one thing I need you to know. The FT here, what's our FT? Our FT actually is an absolute value sine 8 pi t, right? Actually got an absolute value one. But you realize here, my FT, I don't have absolute value. Can you see? I don't have absolute value. You don't know why or not? You don't know why here I don't have absolute value? Is it that I forgot to put down? So do you know why here I didn't put absolute value?
From 0 to 1 over 8.
From 0 to 1 over 8. Why I did not put absolute value here?
Because it's the positive cycle.
Yes, because your sine 8 pi t actually is positive from 0 to 1, 8. All right, actually it's positive. So the absolute value is just itself. All right, so this is the reason. It's actually the reason here why I didn't put absolute value, because in this interval, the absolute value is just sine 8 pi t. It's okay. Then of course you want to say, like that. Then if you want to put absolute value, also can. When you are doing integration, you must remove absolute value. Okay, so you cannot put absolute value and then go and integrate inside absolute value. That is cannot. Okay, so you must remove the absolute value. That's why I remove the absolute value. Then I can go and integrate. It's okay. So this is how it is done. Okay, then we go to AN formula. Now this is actually our AN formula. And same thing lah. This is 0 to 1, 8, right? Yeah. So you can see my FT is sine 8 pi t. And I think you know the reason, right? Yeah, because for t in this interval, your FT, which is the one with an absolute value, actually is just this. All right. Yeah, this is positive. Okay. Yep. Then the next thing is, of course, how do we integrate? All right. How do we do this integration? You know, sine 8 pi t, cosine 8n pi t, right? How to integrate? Now here, actually, to integrate, you need to use some trivial formula that's given. All right. So actually, they give this in the question. This formula is given in the question. So I will apply this. All right. So sine A, so your 8 pi t is your A, and cosine B, so your 8n pi t is your B. All right. Then you do this, and now you separate into 2 terms. All right. Then become like that. So you got this term plus this term. Okay. Now this one is addition. Okay. Now addition, you can integrate term by term. All right. Just now cannot integrate, but now you can integrate. So just go and integrate. Yep. Then so this is your answer, right? So after that, then you just go and put in your Fourier series. You got your A0, you got your AN, right? Then just go and put in. Okay, simplify a little bit. Then write down the first 4 non-zero terms. Now, first 4 non-zero terms. Now, here you already got the first term. Your 2 over pi is already the first term. So you just go and substitute n equal to 1, 2, 3, and so on. Yeah, just make sure that you don't get zero term. If you get zero term, then get to the next value of n. All right. Then you will get the first 4 non-zero terms here. Is it okay? Yeah. Any questions? All right. So this one looks like okay also. So now let's do another summary. Okay, so now I'm going to talk about a half-range series. Right, half-range series. So this one, half-range series, actually the problem is like that. So everybody look at your left side, look at this box here. You see this thing that I boxed up, right? Let's go and look at this. Now, suppose we have a function ft. It is defined for t from 0 to p. Okay. This function is not periodic. Actually, odd or even or not doesn't matter. The main thing is it is not periodic. Yeah. So it's only defined between 0 to p. All right. It's not known to be periodic. Now, it is not periodic. That means you cannot talk about the Fourier series, because Fourier series is for periodic function. So if this thing is not periodic, or actually you cannot write down Fourier series. All right. However, you still want to express it somewhat like Fourier series, because this Fourier series actually is a very useful one. You all study the course 2010 or not? Class, you all study EE 2010, right? Yes, right? So this EE 2010 actually is the whole course is about Fourier series. So therefore, you see our Fourier series is actually used in this signal and system. Okay. So therefore, although the function not periodic, you still want to write it like Fourier series like that. Okay. So how do we do that? Yeah. So how do we do that? So actually, this can be done. All right. So we are able to write ft equal to this. It's actually the Fourier cosine series. All right, but we put it half range only, valid for p from 0 to p. So that's the meaning of half range. All right, so that's why they call it half range series. So this is actually half range. All right, it's not overall t, but it's only for t from 0 to p. All right. And we are also able to represent the ft as the Fourier sine series, also half range. Yeah, so see, this one is also half range, right? T from 0 to p. All right, so actually what we do, all right, how come, this non-periodic function you can write like this, right? So actually, let me explain to you. So the reason is like this. So we have our function here, ft, t from 0 to p, right? Yeah. So suppose this is this line is our ft. So it's defined from 0 to p. All right. Now, how to make it a Fourier series? How to make it a Fourier series? So what I do is this. I want to complete this to 0 to 2p. Not say complete, extend. Okay, I want to extend to 0 to 2p minus p. Now, how I do extension? There are two ways I can do it. One way is I can make it an even function. So if I make it an even function, that means like that. All right, now I see symmetrical, right? Symmetrical about the vertical axis. So now from minus p to p, it is an even function. So this one is even function. Yeah, even function, right? And then this minus p to p, you treat it like one period. Yeah, so you treat it like one period, 2p. Okay, from minus p to p is one period. So you treat it like one period, right? And then this one period is what? This one period is even. Yeah, this one period is even. Okay, and therefore, and then now what you do is that you go and write down the Fourier series of this extended one. This extended one is 1 period, right? You assume it's 1 period. So it's even function. You go and write down the Fourier series of this even function. Okay, and what is the Fourier series of even function? Fourier series of even function is this. All right, it is this one. Okay, this is the one for even function. So then you write, then equal to this, right? But then you don't put it over the whole real line. You only put it valid for t from 0 to p. All right, so that's how you get this one. Then how about the other one? The other one is like that. This time, when you do the extension, you don't make it even. All right, your extension is you go and make it odd. Yeah, so you make it odd, then it will be something like that. So you extend to 0 to minus p, and you make it, minus p to p, you make it an odd function. So this time it is not even, it is odd. Yep. So now you make it an odd function, right? So from minus p to p, well, the period is still 2p, right? You make it an odd function. So you assume that this is a 1 period of a periodic function. And then you go and write down the Fourier series. All right, Fourier series of odd function, right? So this time you are going to get this one, the Fourier sine series. All right, and then you restrict the range. You make it only half range. All right, so therefore you can do this. Is it okay? All right. So this one, we actually call it half range cosine series. And then this one there, we call it half range sine series. All right, then what about the A0, AN, and the BN there? What's the formula? What are the formula? Now, this is actually the one for even function, right? This is the one for odd function, right? So the A and the B here, the formula will be just like here. Just like this one, no? Yep, so same formula here. Is it okay? All right, y'all? Okay, class. So this is our, is it? Yeah. So this is our summary. So now coming to our question. Okay, find the half range sine. Now see half range sine and half range cosine expansion of the following function defined on the given interval. So my ft is 1, 0 to pi, 0, pi to 2 pi. All right, okay, we are going to do this. Now, this is our summary, right? So you see, I'm going to do this. Now, to do all this, you know that in our formula, we need to know the p, right? The small p we need to know, right? Now, what is the small p? Now, the small p here actually is this same p here, right? Now, you see here, t, your ft is defined from t from 0 to p. So that is the small p. You all see, this is actually the small p. This is the very important small p here, right? Your original function is defined from 0 to small p, right? Okay, coming to our question now. What is the small p here? So what is small p? Do we know what is the small p here? If we know, then we can find out. So what is the small p here? What is the meaning of small p? Your function is defined from 0 to small p, right? Yeah. So in our this problem, our function ft is defined from 0 until where? What is the small p? Yeah, class, anyone?
2 pi.
Yes. Actually, it's 2 pi. Is that right? So small p is 2 pi. Now, don't be fooled by this. Don't tell me pi. All right. 0 also counted. This one got 2 parts. So it's actually defined from 0 until 2 pi. So your small p is 2 pi. Is it okay? Right. So if you know this, then everything will be very straightforward. You see, your small p is 2 pi, right? So first of all, let me get the half range sign. So this is the half range sign. Go to the summary. Now half range sign is this one, right? Yep. Summation Bn sine n pi t over p. All right, t from 0 to small p, and my small p is 2 pi. All right, so this is your Bn formula. So over here, you see inside the formula, you see all the small p, right? So the small p is 2 pi, right? So I really want to carry out this integration. So you see, I'm going to integrate 0 to 2 pi, right? But our function is actually in two parts. And you see, it's 1, 0 to pi, and 0, pi to 2 pi. All right, so this one I need to split. So 0 to 2 pi, I will need to split it to 0 to pi, and then pi to 2 pi. Okay, so over here, 0 to pi, your function is 1. Pi to 2 pi, your function is 0. Right? So this is how you do the Bn. Any problem here? Okay, so then you just go and calculate the Bn. And after calculating, put it inside. Okay, so this is your Bn. Oh, yeah, so this is your half range sign. Okay, right. Then the next thing is half range cosine. So this is your half range cosine. Yeah, you can see it's this one, right? Yeah, p from 0 to 2 pi. P from 0 to p, half range. Right, so this is your A0 formula. So I think now you know why we need to split, right? Yeah, that's because our function is defined in two parts. Okay, so this is my an. Well, also integrate 0 to p. So we also need to split. Yeah, you see, split into two integrals. Then we get the an. Okay, well here, because I come to here like last page already, so I have no space to go and write this half range cosine, but we should go and write down. Okay, so this A0, this an, go and put inside here and write down your final answer. Okay, ft equal to, no, just go and write down. Is it okay? Any question?
Prof, why the answer did not include the discontinuity?
The answer didn't include what?
The discontinuity.
The discontinuity.
Yeah,
I
thought it's inclusive of the 0 and 2 pi. Do we not need to include it?
Oh. Wow, that's a good question. No one ever asked that. So yes, you are right. So actually there's a discontinuity here. The discontinuity is actually at pi, right? Everyone can see, actually there's a discontinuity, and the discontinuity is at the pi, right? So the graph, let's go and draw this graph. If we want to draw this graph, so this is your axis. So this is your 0. This is your pi. This is your 2 pi. Okay, so my graph is going to be like what now? 1, 0 to pi. Okay, so this is a 1. And this one is a 0. So the graph is something like this. Okay. Right. So there's a point of discontinuity. When we make it even, when we make it even function, when we extend this, the extension is going to be like that. All right. So this is one period. This is one period, and you can see that there are discontinuity, right? Yep. So the discontinuity actually is here. Yeah, the discontinuity is actually here. So you can go and define at pi at pi, you go and define it to be 1 plus 0 divided by 2 at pi. So you can define your f pi, your f pi, you go and define it to be, shall I go and write your f pi, you go and define it to be 1 plus 0 divided by 2. Okay. Yep. So your f pi, you go and define it to be this.
So for exam, for this question, do we need to find it?
Actually, you should. Actually, you should.
Okay, then one more question is, so if it's x less than instead of less than equal to, then we do not need to include, right?
What is your question again?
If it's t less than pi, instead of t less than or equals to pi, then we do not need to include, right?
Yeah.
Okay, thank you, Prof.
So is that all? Okay. All right. Okay. So we complete the tutorial already. So anyone here want to ask me question?
Sorry, can I ask on questions and on all this
What?
for upcoming tests? Yeah, sorry, give me a second. Let me find the question. Okay, for under the, how do I ask? Is it possible? Let me see if I can send the question.
No, you can share screen.
If you need me to rush it,
I already made you the co-host.
Wait, I can't send it because it's on my iPad. Then I'm on my desktop right now. How do I do this?
it's just easier than chasing people. Thank you. Okay. Bye. Thank you.
Yeah.
You go and log out, then log in from your iPad. Oh.
Okay. I think never mind then. I think a bit hard to share over here.
Okay.
Yeah, okay then. Thank you.
The other day, someone emailed me, say want to ask me. So I said after our tutorial tonight. So that person is not here, is it? So that person not here, huh? Let me go and see my email. See who is the person. Hold on, I go and see who is the person who asked me. Okay, anyone call Lau Ka Hao here? Lau Ka Hao?
Prof Huan, I'm doing cause got some issue here.
You are Lau Ka Hao?
Yeah.
Oh, yeah, Edwin. Yeah.
Yeah.
Oh, you want to ask me something, is it?
Yeah, it's the same question that she wants to ask, but it's like very hard to share screen. Hold on. Okay, I got a question ready.
Oh.
Okay, let me share screen. Yeah, is this question?
Yeah. Lifetime of television tubes.
Yeah, so we are trying to ask about the last part, like how should we actually solve the last part?
Last part?
Yeah.
You mean B2?
Yeah.
Find the probability that the sample standard deviation lies between this and this. Okay. Oh, this one. Probability of S between these two numbers, is it? So
yeah.
that means okay, you hold it. Let's see, full screen. So you want to find this, right? Probability that the S between these two numbers. Between these two numbers, right? The 40 40 point something and the 57 something like that, right? Yep. You want to find this probability. So you S you cannot do that. So what you do is you go and square. Okay, go and square. And then your X is normal. Yeah, you can see that your X is normal. Your X is normal. So that means your n minus 1 S square over sigma square is chi-square. Then you use your chi-square. So you use your chi-square. So you need to have n minus 1 over sigma square, right? N minus 1 S square over sigma square. So then what you do is you put your n minus 1 here. You put you times n minus 1. You times n minus 1. You know, here also times n minus 1. Well, you all know what I'm trying to
minus n minus 1, right? Yeah.
Times n minus 1, then divide by sigma square. Divide by your sigma square. N minus 1, you know the number. Sigma square, you also know the number, right? Sigma square. Sigma square. And like that. So this will become, and this will become,
That's the right minus the left one.
ah,
I mean, like when you
Uh,
find the using the kind
yeah,
of
this is your
table.
chi-square. This
Yeah.
middle one is your chi-square. All right, chi-square between these two numbers. So it's the same as probability of chi-square. Chi-square less than the one on the right minus
On the left.
your chi-square less than the one on the left. The right. This one is the left. You know or not?
Yeah.
The right means this one. This is your right. This is your left.
Okay.
You know? This question very good. Next time I set this question. Maybe next time is this time.
Exam, bro.
Yeah. Good idea.
Sorry, Prof. Just one more question. Because I know binomial is two things pass or fail, right? So if I say I flip a coin, it's also like head or tail. Is it also considered as binomial?
No.
No, why?
I mean, it is a binomial trial. It's a binomial trial. It's a binomial trial because one trial has only two outcomes.
Yeah. So if I flip a coin and then the coin only have head or tail, then the outcome was also only two, right? So it's also considered as a binomial trial, right?
Yeah, it is.
Okay.
Mm.
Then when do I use like the probability of like each different one and like sum up versus I should use binomial? You get what I mean? Because like in front the Oasis, right, it's all just probability and then you minus off, or you draw every possibility, then you sum up.
I believe there are also questions under binomial distribution.
Yes.
So it's a kind of different, right? Because binomial random variable, they always say that it's the number of successes.
Yes.
Number of successes that occur in the n trials of a binomial experiment, right?
Yes.
So therefore, you must see the question, no? So if the question really something like that, they ask you, don't know how many successes are there, or the probability of how many successes, right? Yeah.
Okay, can. Then I understand it. Thank you.
Okay. Well, just now who asked me the discontinuity one?
Me. Why?
Oh, we drink,
Yeah.
Oh, okay.
Why, bro?
No one asked me that before. Yeah, no one asked me that before. So, any more questions?
No more, I think. Thanks, Prof.
I actually got one more, but can I share my screen?
Hold on.
But it's from the Oasis one.
Hold on. Okay. You can share your screen.
Can you see?
Yeah.
Yeah, so I do not know why this, like how do I know when to use the binomial formula for this one?
Then your C is what? 3 of them are accident prone. 3 of them are accident prone. Right?
Okay.
So that means accident prone is like success. Because it's a accident prone or not accident prone, right?
Yes.
So accident prone is like success. So they say people divide into 2 classes, accident prone and not accident prone. So probability that accident prone,
The probability,
40% is accident prone. So there are 7 policy holders, right? So that means this is a BN. There are 7. So that means N is 7. So each one is, that means it's like 7 trials. Each trial is accident prone or not accident prone. You are interested in those that are accident prone, and probability that one is accident prone, a person is accident prone, is 0.4.
I got confused because for the binomial probability, we learn it at the behind part, not under this content.
Oh,
So I don't know why this question we need to use that. Is there another way?
maybe you got part A, part B one.
Sorry?
Well, I see that this one is C, right?
Yes.
So maybe you got part A, part B.
The part A is all this.
Yeah, so these are some other things, right? Maybe it's on what total probability or Bayes theorem partition all these, right?
Yes, correct.
Yeah, but the last one is actually binomial.
Oh, okay. Can. Thank you, bro.
Okay. Wow, tonight very few people. Well, I think maybe next week no one.
No lah, prof, cause exam on Saturday, then all try to mark.
Really?
Yeah, our math exam is on Saturday.
Yeah, I know.
Yeah, so everyone is chowing the Oasis already.
Oh, really?
Prof, why the Oasis so many questions?
Yes, yeah, I want to cry already.
Well, the Oasis questions are quite difficult, is it? Yeah, should be.
It's not difficult, it's a lot.
Oh, that's why I say no need to do all. You every topic do one more, and then even if you cannot finish one now, wait till exam. You every topic you can go and try one.
Oh yeah, I got one more is for the later part forest series content, do we get Oasis question also?
Oh, that one is no.
Okay.
Then you no need to you no need to do until so difficult.
Sorry, can I just ask bit like this Saturday the exam, right? Is it like how would it be like cause don't have anything that says about its structure. Like the structure of the Oasis, am I supposed to have like all blanks, all filled in blanks, or is there MCQ? Is it guided or not guided?
It's fill in the blanks, and some will be MCQ.
Okay.
Yeah.
Thanks.
Okay, can already So now you all can go to sleep lah. Oh, class okay or not? So we all go to sleep. Okay, class.
Prof.
Okay, bye bye.
Thanks, Prof.
Bye bye.
Okay, bye bye.